So let's start, I think. So welcome to this session on actually combining learning and solving. Interesting one, I guess. First paper will be by Ronald van Driel, Emir, Demirović, and Yorke-Smith on learning variable activity initialization for lazy close generation solver.
Welcome to this talk about learning variable activity initialization for lazy clause generation solvers. And this work is by Ronald van Driel, together with Emir and myself at TU Delft in the Netherlands. Here's the takeaway message from this paper. We want to improve the performance of Chuft, an example of a lazy clause generation solver, and the way we improve the performance is by influencing how the LCG solver chooses variables, the variable selection heuristic. In a bit more detail, we improve the performance of Chuft, this LCG solver, by using machine learning to predict unsatisfiable cores. We use those predictions to initialize the VS-IDS variable weights used by the solver. Why? What's the motivation for this work? Well, there's been plenty of interest recently in combining machine learning with operations research, or with constraint programming, or with Boolean satisfiability. And there's been work in the past on combining SAT and CP, in particular, lazy clause generation. What about combining machine learning with lazy clause generation? Of course, in some sense, LCG solvers have some learning built in. We're asking, what can we add to that? The inspiration for this paper comes from the work on doing something similar in Boolean satisfiability. So this paper, NeuroCore. And we're going to adopt the same idea of learning unsatisfiable cores and using that to initialize part of the solver. Here's how it works. We're given a problem instance. Chuft, the LCG solver, then does some initialization, and in particular it chooses values for the VS-IDS weights. And by default, the initial values are 0, uninformed. Once Chuft is ready, it then does search. So it does conflict-directed solving, and that leads to a solution. So here's the idea of the paper. Rather than initializing these VS-IDS values to 0, we're going to initialize them to values learned by machine learning, learned offline beforehand. In more detail, how do we achieve this? Well, first, offline, we're going to train on unsatisfiable CP instances. With our trained learned model, we're going to predict unsatisfiable cores for a given satisfiable instance. So given an instance, we're going to predict which variables are in at least one unsatisfiable core. That prediction we'll then use to initialize the VS-IDS scores, and then Chuft does its regular solving after that. So the only change we make is initializing these values. We don't touch Chuft's regular solving, regular built-in conflict learning, regular heuristics, just the initialization. Now for this to work, we need to train a model, and so we need data. And we need both satisfiable and unsatisfiable CP instances. Now unfortunately, we couldn't find any public unsatisfiable datasets, so we made one from the mini-zinc benchmarks. We solved the entire mini-zinc benchmark library in the case of optimization problems. Once we knew the optimum, we then adjusted the objective function value with a constraint to ensure unsatisfiability. That gave us an unsatisfiable instance, and then we could use the built-in mini-zinc tools find mus to give us the unsatisfiable core from each instance. Details of this are in the paper. Once we have data, we can train an ML model. And this is what our model looked like. It's a graph convolutional network. The nice thing about a GCN is it captures the graph-like nature of the CP problem. The output is a 0-1 number for each variable, which corresponds to the probability that that variable is involved in at least one unsatisfiable core for the CP instance. What are the features used by our ML model? We have categorical features and numerical features. The categorical are, for example, is a variable a Boolean or not? The numerical features are to do with the range of the variable's domain. We use the output of the graph convolutional network to initialize the VS-IDS scores. How? We say if the variable is part of an unsatisfiable core, then the label is 1, otherwise 0. Again, details are in the paper. So now we can put the pieces together. We can use our learned model to initialize these variable selection heuristic initial values in Chuft. Let's compare. Let's compare two learned versions, that's Chuft 1 X and Inc, with baseline untouched Chuft 0. Now the two learned versions are, do we train excluding the instance class we want to test on, or including it? So the excluding version of Chuft has a harder job because it's never seen instances from the problem class we're going to test on, whereas the including version has. Of course, we test on instances that are unseen. We'll do 100 runs on the 4 largest problem classes from the mini-zinc benchmarks. Here are the results. You can look at them in more detail in the paper. The 4 problem classes of these, the biggest is MR-CPSP. And if you look at the top left graph, what we're seeing here is the 3 different solvers, the baseline and the 2 learned versions. And we're looking at average total runtime. So lower is better. And you can see that Chuft 0, the baseline on the left, has higher average runtime than both of the learned versions. The story is a bit similar on bin packing, but it's not so clear on the other 2 problem classes. Here's another way of looking at it. Here we see the 3 Chuft versions. Again, the baseline, that's on the left in each case, so that's in blue now, and the excluded and included versions. And here on the vertical axis, we're now showing relative runtime. So again, lower is better. And we show the confidence intervals here. So we see on MR-CPSP, we're getting an improvement of 2 and a bit% across the problem instances. Whereas fast food were actually slightly slower in the learned versions, but it's not statistically significant. Whereas for MR-CPSP and for bin packing, it is a statistically significant win for Chuft with learning. Let's summarize. We've injected one piece of learning additionally into an LCG solver, just initializing the values of the VS-IDS heuristic scores for each variable. Nothing else changed. And we have promising results on 2 problem classes, MR-CPSP and bin packing, a robust, statistically significant increase in average runtime of 1 to 2%. We saw little difference between the excluding and including learned versions. What that says is the excluding version is doing about as well as the including version, so that means we have generalization. It seems our learned model has generalized across the instances of the mini-zinc library and is able to do well on unseen problem class. The other 2 problem classes, we didn't see an improvement, in fact slightly worse in one case. And probably that's because there were fewer instances, and perhaps in the other types of problem instances, there wasn't things similar enough to these 2. But again, we were not worse in terms of the statistical test. And an important point is what we've done here is compatible with other improvements to an LCG solver. We've injected a little bit of machine learning. Additionally, we changed one thing, but everything else you could still improve using machine learning, or of course other approaches. And that brings us to the future work. We had our graph convolutional network separated from the LCG solver. It'd be interesting to embed the learned model within the solver itself. And that would open up some more things you can do. Be interesting to look at more data, more problem classes beyond the mini-zinc benchmarks, and also at other ML models. We only tried the GCN, and it worked quite nicely. One interesting idea would be to periodically refocus. So consider reinitializing the values of the VS-IDS variables. We only look at the start. What about later in the search? Other ideas for using machine learning would be to learn the initial parameters for the LCG solver. There's many parameters to Chuft. We essentially only look at one thing. Then lastly, we predict whether a variable is involved in some unsatisfiable core. You could try directly predicting no-goods. That would be an interesting direction and a tighter coupling with how the LCG search works. So in summary, this paper improves the performance of Chuft, an LCG solver, by using machine learning to predict unsatisfiable cores and using those predictions to initialize the VS-IDS variable weights. Thank you for your attention.
Do we have questions?
Yeah, I got a few. I don't know. I guess I saw Emir on the session. Oh, Neil's there. So I'm just amazed that this works, because after 1,000 conflicts, the VSID score essentially decays so quickly that this has to be giving you a lot of advantage right in the beginning of the search, right? And I'm just wondering why you chose to only give them one. Why not 100 or 1,000? Because I know that it's all relative, but wouldn't they decay so quickly so that we wouldn't see the advantage of this? Or are you making it hard for yourself, I guess, is the thing. Maybe you did some other experiments.
Yeah, good questions. Yeah, no, so we didn't do more things than this. So one of the students just wanted to look at one thing, so only the initialization. And you're right, the values do decay, and hence some of the future work could be to look at reinitializing or look at values later. So really the inspiration was this paper in SAT, Yorke, and Ronald saw that and thought, okay, can I do the same thing for LCG? And that's what they did in their paper. So he said, okay, let me do the same thing here. And it's kind of nice that it works. It's a bit surprising. I mean, the nice thing is it's really quite simple. I mean, we've injected a little bit of ML, but it's not very much. And it gives a nice sustained win. So yeah, I think there's lots of opportunity to add more things to it. And also to explore more about how those values for these VSID values change over time.
Yeah, I mean, I think we sort of know that those initial VSID values are completely useless. And in fact,
right.
There's the possibility if you just use VSIDs by itself, that it sort of goes off the rails, actually. So I'm sure that part of what you're seeing is less off the rails, but yeah, I was surprised that you could get that much result. But I guess another thing which would interest me is combining it with, so we would often use hot start, where we'd use a program search initially so that we'd get some activity out of that. I'm wondering if you can combine this with hot start. That would be interesting.
Yeah, I think so. I think it'd be very interesting. Yeah, I agree with that. Yeah.
Okay, I have a question on the Zoom chat. If the unsat instances are created by changing the optimum, won't the graph be the same?
Won't the graph be the same as in the constraint graph? Yes, it will. I don't fully understand the question. Is that a problem, that the constraint graph's the same? So I mean, all we want to do here is to make sure the instance is unsatisfiable. So the trick that Ronald used is to just adjust the optimal value. and that ensures it's unsatisfiable because we know we found the best solution and we're worse than that. Then sat and unsat have the same graph features.
But I think the point is that when we set the objective, it's now an unsatisfiable problem, and then compute these cores that are necessary for the learning process. So it's not so much about the features. It's simply that we can generate these cores, meaning that the subset of constraints can simultaneously be satisfied. So we use those.
Right. So it depends on because I mean one of your features was the graph, right?
Yeah, constraint graph, yes.
Right. So then if the graph is the same for set and unset, at least in your test set, in your testing, right? Then isn't the graph like useless?
We didn't do a feature analysis. That's true. I would assume that having the graph structure is useful because it allows the GCN to look at how the constraints and the variables are connected to each other. You're right. I mean, what we didn't do is try the same thing but not have those features. I think my hypothesis is it would be worse.
Well, I mean, there are various explanatory techniques you can use to see, the importance of the graph feature, blah blah blah.
Yeah, we could look into that.
Discussed yesterday.
Yeah, we didn't do that.
Okay, so I had a question about can we learn polarity of these Boolean variables, but let's answer in the chat.